Welcome back to the deep dive. This is the show where we cut through the noise, we get past the marketing hype, and we go straight to the technical core.
And we are, of course, a part of Neural Intel. To stay updated on everything we cover here, you can visit our webpage, neuralintel.org, or check us out on YouTube.
Today, we have a really fascinating set of sources. We are diving deep, and I mean really deep, into Zippu's new flagship model, GLM-4.7. It was announced on December 22nd, 2025.
That's right. And this isn't just, a minor version bump.
Yeah.
The developer docs, the community chatter. Everything points to a pretty fundamental re-engineering. It seems to be all about stability.
Okay, so let's set our mission for this deep dive. We're doing a full technical dissection. We're going to analyze the core specs, the reasoning architecture, which really seems to be the heart of this thing.
Absolutely.
The benchmark performance, and of course, the nitty-gritty implementation details. What does it actually take to get this monster up and running?
And our focus, to be really clear, is on GLM 4.7's stated mission. Agentic coding, it's a 358 billion parameter model. And yeah, that scale is impressive. But the real story here is the operational overhaul.
An overhaul for what, specifically?
It's engineered for long-range task planning, for complex tool use. The key technical takeaway, really, is that they've delivered this significant and, frankly, necessary overhaul of its multi-turn reasoning mechanics. And that is the absolute precondition for building a reliable, autonomous agent.
That sets the frame perfectly. We are not here to talk about poetry generation. We're talking about fixing real-world bugs, integrating services, across huge code bases. So let's start with Section 1. Let's establish the fundamentals of this new flagship. First thing that jumps out is just the sheer scale of it, 358.0 billion parameters. But maybe even more striking is that the sources confirm it's under an MIT license.
Right.
For a model of this size, claiming state-of-the-art, what's the strategy there? Why release these massive open weights?
The MIT license is a huge commitment. I mean, financially, infrastructurally, usually a frontier model like this is locked behind a very expensive API.
Or a really restrictive license, at best.
Exactly. So releasing 358 billion parameters under MIT, it suggests Zippu is playing a longer game. It's not just about winning benchmark battles. It's about establishing an entire ecosystem.
They want people building on top of 4.7.
They want the community to build agent infrastructure on 4.7. It drives adoption. It validates their specific architectural choices, even if it costs them a fortune to train and align the base model in the first place. For the developer, well, it means true. Deep customization is on the table.
Assuming you have the hardware.
Assuming you have the computational muscle, yes.
Which brings us to capacity. The model has this gigantic 200K context length and 128K maximum output tokens. We see context windows getting bigger all the time, but why is this specific 200K number so important for this whole agentic coding mission?
It's the difference between generating a single function and managing an entire project state. If you're just writing a little script, 4K context is fine. But for an agent handling a complex task, something with dozens of steps, multiple tool calls, that context window has to be its working memory.
And its knowledge base for the task at hand.
And it's knowledge base. It's everything.
Okay, let's get specific, though. Let's say I was using GLM 4.5, which had, 100K context? What's a real-world coding task that fails at 100K but suddenly works at 200K?
Okay, good question. Let's build a scenario. Imagine you tell the agent, refactor our auth flow to support OpenID Connect, and make sure you update all the legacy API endpoints that still use the old GWT schema.
Okay, so that's not one single action.
Not at all. It's a long horizon task. The agent first has to read, let's say, 50,000 tokens of the existing authentication code just to understand it. Then it might pull in another 20,000 tokens from the OpenID Connect documentation to learn the spec. Now it starts actually changing files. It updates the database schema, it changes the API routing, it adjusts, 3 different React files for the UI.
And it has to remember every change it makes.
That's the key. If the context window is too small, by the time it gets to that third React file, the initial context, the OpenID spec, or that crucial old JWT schema, it starts to fall out of the window. It gets pushed out.
It's context dilution. The agent basically forgets why it started the task in the first place.
Exactly. It loses the plot mid-refactoring. 200K tokens lets the agent hold on to not just snippets, but entire complex code bases, the full history of all the changes it's already made, all the internal reasoning traces from this new preserved thinking thing we'll get into.
Nice.
Without that deep context, the agent loses track of global constraints like, dependency versions or how files relate to each other. You get unreliable code, or worse, subtle logical bugs that are a nightmare for a human to track down later. 200K provides this persistent, omniscient view of the whole environment. It's the technical prerequisite for doing this stuff autonomously.
And that leads us right to the core claim. Agentic coding. The docs frame it as focusing on task completion, not just code generation. How is that architecturally different?
It's a shift in the optimization target. The model isn't just trained to predict the next token of code. It's trained and fine-tuned to automate the whole developer workflow.
So you're saying it's trained to understand intent.
Yes. It's designed to handle requirement comprehension, understanding what you actually want, even if your prompt is a bit vague. Then, solution decomposition, breaking that vague idea into, say, 15 concrete executable steps. And finally, multi-technology stack integration.
Let's stick with that last one, the multi-tech stack part. That sounds computationally very difficult. What does it mean in practice to generate structurally complete executable code frameworks?
The goal here is to solve what you could call the glue code problem. So imagine you ask the agent, build me a minimal, secure user registration service. Use React on the front end, Flask on the back end, and validate the data before you store it.
Okay.
With older models, you might get a decent React component, or you might get a decent Flask file. Maybe.
But you'd never get both working together out of the box.
Right. You'd have to stitch them together yourself. GLM-4.7's goal, based on the sources, is to generate an entire project directory. A package.json with all the dependencies listed, a working app.py Flask file with the API routes already defined, a user registration.jsx React component that already knows the correct endpoint URL to call.
And all the boilerplate, like cores, headers, and environment files.
All of it. The idea is to generate a coherent system that is executable the moment you receive it, not a box of parts that takes you 3 hours to assemble. That requires a much deeper understanding of system architecture and how different languages and frameworks interact. It's a huge leap.
And they're not just stopping at code structure. They're also talking about web UI generation with this brand name vibe coding. I'm always a bit skeptical of marketing terms, but what's the actual technical optimization here? How do you get aesthetically pleasing code?
Vibe coding is, yes, it's a bit colorful, but the technical idea behind it is solid. They're improving the model's grasp of visual and aesthetic constraints within the code itself.
How do you even train for that?
Through better supervised fine-tuning. You use paired datasets that link structured code HTML, CSS, React components with human ratings for aesthetic quality.
I see.
So technically, that means the model learns to generate default solutions with better, more consistent design principles. It uses modern layouts like Flexbox or Grid correctly. It picks colors that work together. It establishes a clear typographic hierarchy.
So it's about saving time on that endless loop of small style tweaks. If the first draft is visually 90% there, you save a ton of developer time.
That's it, exactly. For quick prototypes, if the form or the dashboard it generates is already near ready to use, you waste fewer tokens and fewer human hours on subjective fixes, like, move that button 2 pixels to the left. It just raises the quality baseline of the initial output.
And this idea of high-quality defaults seems to carry over into professional document generation, too. They specifically mention Office documents.
Yeah, and the metric they give is incredibly specific, which I love because it tells you exactly what they were optimizing for. They say PPT 16.9 compatibility went from 52% in the last version all the way up to 91%.
That's not about writing better bullet points. That's about layout.
Precisely. It's about respecting rigid structural constraints. When an automated system makes a presentation, compatibility means making sure images don't get squashed, text boxes don't overflow the slide, and the company template is applied consistently across all 50 slides. A 91% success rate there means the model can handle layout and structure reliably, which massively cuts down on the human QA time needed for this kind of auto-generated content.
So the theme is consistent across everything, whether it's full-stack code, a web UI, or a PowerPoint deck.
Right.
It's about structural completeness, consistency, and reducing the cost of manual work after the fact.
Right. But as you said, all of these complex multi-turn things depend entirely on rock-solid stability. If the agent forgets its own plan, that 200K context is worthless.
Which means they had to do something fundamental to the reasoning engine.
They did. That need for stability forced a total rethink of the operational architecture. We really need to look under the hood.
Okay, let's do that. Let's transition to our branded segment and inspect the neural engine that's driving this whole thing. Welcome to our neural signal check. This is where we explain why a new development actually matters at a deep technical level. And with GLM 4.7, the performance gains are all rooted in a strategic redesign of its internal mechanics. Before we get to the new stuff, let's talk about the technical debt they were trying to fix.
Yeah, we have to talk about the problems with GLM 4.6. Despite its size, it was known for being, well, inconsistent. The community was very vocal about its poor multi-turn instruction following. You'd give it a 10-step plan, and it would forget the goal by step 5.
But it was more than that, right? It was about effort.
That was the critical failure. Inconsistent reasoning effort. Sometimes 4.6 would waste a huge amount of compute generating this long, complex, sophisticated reasoning trace for a really simple question.
And then when you actually needed that deep thought,
It would fail. On a genuinely hard problem, it would give you a single useless bullet point. Exactly when you needed it to think deeply, it just wouldn't.
that kind of unpredictability is a killer for any real production agent. You have to be able to rely on it, especially for the hard problems.
That's the mandate for 4.7. So they kept the existing interleave thinking, which is the idea that the model should think before every response or tool call. But they added 2 major new capabilities to fix the state and effort problems. Let's start with the first one, preserved thinking.
Okay, preserved thinking. Let's get into the mechanism. How does the model actually achieve this, and why is it better than just letting the massive 200K context window remember everything?
The mechanism is actually pretty elegant. In a multi-turn conversation, the model automatically saves all of its internal reasoning blocks. The chain of thought or tree of thought traces from all the previous assistant turns.
So it's not just saving the final answer, it's saving the workings out.
Exactly. And that reasoning content is explicitly tagged, it's preserved in the conversation history, and it gets returned in the API calls. This allows the developer's application to feed that reasoning right back into the context for the next turn.
It's maintaining its own internal monologue.
Okay, but here's the challenge I see. If you're saving all that reasoning, aren't you just massively inflating the number of input tokens on every subsequent turn? Doesn't that get really expensive and kind of negate the efficiency?
That is an excellent and very necessary technical question. And on the surface, yes, you're adding more tokens to the context window. But the operational cost of rederiving complex reasoning from scratch is vastly higher than the cost of just transmitting and caching the reasoning that already exists.
Okay, explain that trade-off.
Think about an agent debugging a complex software issue. The reasoning it needs for step 25 might depend on a conclusion it reached way back at step 5. If the model has to regenerate that reasoning from scratch, that's a huge compute cost and it adds a lot of latency.
And it might make a mistake the second time. And it's more likely to generate a worse result. By preserving the reasoning block, the model can just reuse the cache logic. This dramatically improves the KV cache hit rates for those reasoning segments, and in the long run, it minimizes the total computational cost. It turns a series of expensive, separate calculations into one continuous, stateful process. You're reusing intellectual capital.
That makes a lot of sense. It transforms the agent from just a reactive system into one with a genuine, persistent memory of its own strategy.
That's the core realization. An agent system that can't maintain a consistent internal state is just fundamentally brittle. Preserved thinking provides that reliable, persistent state. It's the key.
Okay, now let's look at the second new feature, turn-level thinking. If preserved thinking is about stability and continuity, what problem does this one solve for the developer?
Turn-level thinking is all about control, specifically developer governance and cost optimization. The mechanism lets you control the reasoning computation on a per-turn basis, even within the same conversation.
So you can turn the deep thinking on and off.
Exactly. This is crucial for any real application that has a mix of easy and hard tasks. You can explicitly enable or disable that deep thinking feature for any given request.
You're giving the developer direct control over the trade-off between stability and latency.
Precisely. Let's say your agent is running a sequence. Turns 1 through 5 might be the heavy lifting, decomposing the problem, making a complex plan. You need thinking enables for that.
Right.
But then turns 6 through 15 might just be simple, lightweight queries, like getting a list of file names or doing some basic formatting.
Yeah.
You can disable thinking for those 10 turns.
And you get faster responses and lower costs.
Exactly. And then you can turn it right back on for turn 16, which might be the final validation step or a heavy debugging task.
There's a really critical architectural decision here that the sources point out. Thinking is now on by default in 4.7, which is the opposite of how it was before. Why would they do that? Aren't they just forcing a higher cost on every single turn?
That is the right way to read that shift. I think what ZPU learned from 4.6 was that its inconsistency, the way it would just randomly fail on a critical step, was a poison pill for anyone trying to build a reliable agent.
So they're enforcing a quality floor.
They're establishing a guaranteed minimum floor for accuracy and stability. By making the reasoning pathway the default, they're prioritizing reliability over raw speed. The turn-level control then acts as a sophisticated escape hatch. It lets the developer choose to opt out of stability for speed on non-critical tasks.
Instead of having to constantly remember to opt into stability for the important ones.
Exactly. It reverses the burden. The new assumption is, your task is complex and requires stability. Now, prove to me you can simplify it to save costs.
That's a much safer default for production systems. Okay, we also need to look at how this model handles real-time tool use, specifically the streaming features.
Yeah, the focus here is all about reducing the perceived latency for the user. GLM 4.7 adds support for real-time streaming output during the tool execution process. You have two flags, stream true, and the important new one, tool stream true. This is a small technical detail that makes a huge difference to the user experience.
Okay, break down the implementation of toolstream true. What's the benefit?
It allows for the real-time retrieval and concatenation of the tool call's parameters, specifically the delta.toolcalls.function.arguments part of the output.
Give me an example.
Imagine an agent needs to call a complex database query tool, and the parameters are a big JSON object with lots of filters and sorting rules. In the past, you'd have to wait for the model to finish generating that entire, say, 500 token JSON object before your application received anything.
Your UI would just be sitting there with a spinner.
Exactly. Now, as the model generates that JSON token by token, your application receives those tokens in real time.
So the front end can react immediately.
Yes. Your application isn't just sitting idle. The UI can start preparing the API call structure, or it could show a message to the user like, executing database query, and even display the parameters as they're being generated, all before the model has technically finished its turn. It just makes the whole interaction feel much more responsive.
So the big takeaway from this neural signal check is that 4.7 is really a re-architected system. It's all about managing internal state and giving developers fine-grained control over the reasoning process for these complex multi-step tasks. It's a stability-first model.
It's a stability-first model that also promises some pretty big performance gains. Let's see if the benchmarks actually back up that heavy architectural investment.
All right, let's get into the numbers. The fact that they released 4.7, instead of jumping to the 5.0 everyone expected, that immediately told us something.
It did. It suggested the focus was on refinement, not a whole new base model. The performance gains we're about to talk about. They're a technical showcase of what you can get from pure optimization. Better supervised fine-tuning, better reinforcement learning, applied to the existing architecture.
They didn't build a new engine, they just perfected the fuel injection and the timing.
That's a good way to put it.
Yeah.
The SFT and RL phases were absolutely crucial. For agentic coding, SFT means feeding the model massive data sets of not just the final correct code, but the entire step-by-step process, the planning, the tool use, the debugging logs.
The whole thought process.
The whole thought process. Then RL fine-tunes it against feedback, rewarding outputs that are stable, efficient, and correct. This is how you validate a new reasoning architecture.
So let's start with the core coding benchmarks. GLM 4.7 is claiming the top open source spot against models like Claude Sonnet 4.5.
Let's look at SGLang.Join verified first. This is, I would argue, the most relevant real-world coding benchmark we have right now. It's not about writing code in a vacuum. It's about producing verified fixes for actual GitHub issues.
And the score?
GLM 4.7 hit 73.8%. That's a 5.8 percentage point improvement over GLM 4.6, which was at 68.0%. That's a really substantial jump.
Why is a benchmark like SWE-Bench so much better for testing an agent than, say, an older one like Human Eval?
Human Eval is great, but it typically tests isolated function generation. You get a clean problem, you write one function. SWE-Bench forces the model to deal with the messiness of the real world.
Ambiguity.
Ambiguity. Complexity. The agent has to read and understand a bug report, which is often written poorly by a human. Then it has to find the bug in a large existing code base. And finally, it has to generate a fix that actually passes the project's existing test suite.
It's the full end-to-end task.
It's the full agentic loop.
Yep.
Comprehend, plan, navigate, execute. That 5.8% jump is hard proof that the new stability and context management features are delivering value on these difficult, realistic problems.
And what about the multilingual performance? That's always a big question for global teams.
The jump here is frankly staggering. On SWE-Bench multilingual, the model scored 66.7%. That is a massive 12.9% improvement over the previous version's 53.8%.
A 13-point jump. That's not just more data.
No, that suggests a very dedicated SFT effort. It means they didn't just feed it more English Python code. They must have poured resources into creating multilingual alignment datasets, training the agent to understand complex requirements written in other languages and apply them to standard code bases. That's a huge technical enabler.
Okay, so it can fix bugs in multiple languages. What about just using the system? We have Terminal Bench 2.0.
This is the litmus test for DevOps agents for automated scripting. It measures how well the model can handle tasks in a command line terminal. Executing commands, managing environment variables, parsing logs, handling errors.
And the number here is?
41.0%. A huge 16.5% jump over 4.6's 24.5%.
16.5%. That's not incremental, that's transformative. What kind of specific skills do you think they targeted to get a jump that big?
A leap like that points to a few key areas. Better understanding of multi-line shell commands, for one. A greater ability to correctly pipe the output of one command, like grep, into the input of another, like awk.
And error handling. That's always where these things fall down.
That's what I think is the crucial part. Enhanced error detection and remediation. A common failure for older models was to just give up if a command returned a non-zero exit code. This gain suggests the new reasoning engine is much better at diagnosing and recovering from command failures. And for autonomous DevOps, that is absolutely non-negotiable.
Okay, now let's connect this back to Section 2. What about the benchmarks that directly test the new reasoning architecture, the tool use benchmarks?
Let's start with Bench. This one is designed specifically to test complex interactive tool use, the whole chain. Reasoning, selecting the right tool, generating the right parameters, and then integrating the result. GLM-4.7 scored 87.4% here.
And the improvement?
It's a 12.2% jump from 4.6. This gain right here is the statistical proof of concept for preserved thinking and turn-level thinking. You simply cannot get that kind of jump in multi-step tool reliability unless you have a consistent internal state and predictable reasoning.
And we also saw a jump on web browsing tasks with BrowseComp.
We did. It hit 67.5%, which is up 10 points. And the benchmark specifies this is with Context Manage, which is designed to stress test how well the model manages its context during long tasks, like navigating a website or filling out a complex form.
So that 10-point gain is direct evidence for the utility of the 200K context window.
It is. When an agent has to navigate 20 different web pages to find some information, that gain is compelling evidence that the 200K context, combined with the stateful preserved thinking, is working. It's retaining the mission-critical information across all those turns instead of suffering from that context dilution we talked about.
This all leads to what I think is the most interesting technical finding in the whole release. The number is on the Humanities Last Exam, or HLE, benchmark. The docs present a gap here that really needs a closer look.
Yes. The headline number is very impressive. 42.8% on HLE with tools enabled. That's a massive 41% increase over what GLM-4.6 could do on the same metric. That score puts it right in the same league as other frontier models.
The critical part is when you look at its raw, unaided ability. The HLE score without any tools is only 24.8%.
Right.
That is an 18-point gap between what it can do on its own versus what it can do with its tools. What does that technical delta tell us about the nature of this model's intelligence?
That gap is the technical fingerprint of the entire 4.7 design philosophy. The raw-based model's reasoning is solid, 24.8% is not bad, but it's not state-of-the-art. The intelligence isn't coming from just having more raw knowledge baked into the weights.
The intelligence is in how it uses its tools.
That's it. The jump to 42.8% when it has access to a code interpreter, a search tool, and can integrate the results, that demonstrates the incredible technical effectiveness of its improved function calling, its interleaved thinking, and its state management.
So essentially, GLM 4.7 isn't necessarily a smarter raw thinker than its rivals. It's a vastly superior planner and executor.
That's the perfect synthesis. It knows exactly when it's out of its depth, when to engage an external resource, and critically, it has the internal state management needed to integrate the results from that tool back into its overall plan without losing coherence.
The intelligence lives in the metacognitive architecture that governs execution, not just in the neural network itself.
Yes, and it validates their whole strategy for this release. They prioritized architectural stability and control over just pre-training a bigger base model. The biggest reasoning gains are almost entirely agentic gains. It's a pragmatic model, optimized to get things done. The era where a single MMLU score was the only thing that mattered is over. Now we're judging models on their ability to reliably complete complex tasks.
But that level of engineering, while it gives these massive performance gains, it comes with a pretty big price tag.
A very big infrastructure cost.
Yeah.
Which means we need to talk about the realities of actually deploying this thing.
So we have the architecture, we have the performance. Now let's get down to brass tacks for the people listening who actually want to use this open model. Let's talk technical deployability, 358 billion parameters. What's the real-world hardware barrier here?
The barrier is substantial. This is not for hobbyists. Community sources are saying that just to run the model, you need a serious amount of memory. Specifically, to run the 4-bit quantized version, which is a common way to save space, you need just a bit more than 182 gigabytes of memory.
And that's assuming a decent KV cache size, right?
That's assuming a decent KV cache, which you absolutely need to take advantage of that 200K context.
Let's unpack that trade-off. Why is the KV cache so demanding for this model in particular?
Well, the KV cache stores the computed key and value vectors for all previous tokens in the context, so you don't have to recompute them on every new token. When you have a 200,000 token context window, which is massive, the size of that cache scales linearly. It gets huge.
And if you skimp on the memory, you have to shrink the cache.
And if you shrink the cache, you have to truncate the context, which effectively neuters the main selling point of the model. That 182 gilob figure, that's the calculated overhead for the 358 billion parameters, plus the cache you need for high-throughput, long-context operations. It's the memory wall you hit with this kind of state-of-the-art agent architecture.
The documents also mention an alternative configuration, a higher performance one.
They do. For optimal speed and numerical stability, which is really important for agentic tasks where you need high precision in your tool parameters, they recommend running the FP8, the 8-bit floating point version.
And the hardware for that.
To run FP8 with a 160K context, you need a setup with 4x96 GB GPUs.
So 4 A100s or H100s.
At least. And that highlights the trade-off perfectly. You're using multiple cards for tensor parallelism to get the speed, but you need that massive combined VRAM of the 4x96 GB to avoid hitting the memory wall from the giant context window.
So yes, the weights are open, but peak performance is really restricted to people with access to serious compute clusters.
That's the reality of it. But having the weights on Hugging Face and Model Scope is still a huge benefit for research. Yeah. And the documentation is very clear that they support popular inference frameworks like vLLM and SGLang.
Let's do a quick deep dive on the configuration there. If I'm a developer and I'm setting this up with vLLM, how do I make sure I'm actually using the new reasoning features correctly?
This is where the documentation gets really specific, which is great. The new thinking modes have unique token structures, so the inference engine has to know how to parse them. For vLLM, you have to use specific flags: tool call parser GLM-4.7 and reasoning parser GLM-45.
Wait, why is the reasoning parser still GLM-45?
Good catch. It's because the basic structure of interleaved thinking was introduced back in the 4.5 release. The tool call parser, though, that has to be GLM-4.7 to handle the new streaming and complex tool outputs that are specific to this version.
Okay, that makes sense. And what about SGLang? Any special considerations there?
SGLang needs similar parser configs, but the docs also include flags for really high-throughput deployments. They show an example server launch that uses 8-way tensor parallelism for max speed, and crucially, they include flags for speculative decoding.
Like EGLE.
Exactly, like speculative algorithm EGLE. This is really the cutting edge of serving these huge models. You use a much smaller, faster model to generate draft tokens, and then you have the big 4.7 model, just verify them in parallel. It's a key strategy to get low latency from a model this big.
That level of detail really shows the high technical bar for deployment. Okay, let's switch to the API side. What's the key constraint for developers migrating from an older version, besides just changing the model name?
There is a really critical technical note about the sampling parameters. The docs explicitly warn that temperature, which defaults to 1.0, and top, which defaults to 0.95, should ideally not be adjusted at the same time.
Let's go deeper on that. Why is that a problem? What's the technical mechanism that makes adjusting both at once so bad for a model like this?
Okay, so temperature directly changes the shape of the probability distribution for the next token. High temperature flattens it out, making it more random. Top, or nucleus sampling, works differently. It prunes the list of possible next tokens, only sampling from the smallest set whose combined probability is above p.
So you have two different knobs controlling the same output distribution.
Right, and when you turn both at once, you can get chaotic, unpredictable behavior. You're introducing a kind of structural noise into the sampling. For a model that's been so heavily optimized for stability and reliability in agentic tasks, that's the last thing you want.
You want it to converge on the correct answer.
You want it to converge reliably. So their advice is basically choose one. Use temperature if you need creativity. Use top if you need stable convergent output like cloud. Forcing you to choose helps maintain the model's predictable behavior, which is everything for a multi-turn agent.
That clarifies why they'd include such a strict warning. It's a stability guardrail. Okay, and how do we use that new turn-level control? How do you force deep thinking on a critical step via the API?
So while thinking is the default now, if you have a really critical step, say, generating the final system architecture, you want to absolutely guarantee it gets maximum computational effort, you can include thinking type enabled in your API call. That forces the highest level of accuracy and stability for that one specific request.
Without slowing down all the other simpler turns around it.
Exactly. And just to round it out, for the streaming, developers have to enable both stream true and tool stream true. And then your application logic has to be built to handle that streaming output chunk by chunk, concatenating the delta.tool calls arguments as they arrive. It's a bit more work up front, but the payoff in responsiveness is huge.
It's clear that from the 4x96 Jerry GPU requirement down to these specific API flags, this is a highly specialized, enterprise-grade agent engine. Hashtag tag tag outro. We have covered a huge amount of technical ground today in our deep dive on GLM 4.7. Let's try to synthesize the three big technical areas that really define this release. First, there's that strategic pivot to agentic coding, to task completion, which is all enabled by the visibility that massive 200K context window provides.
Second, the completely re-engineered reasoning architecture from our neural signal check, the enhanced interleaf thinking, and those critical new stability mechanisms. Preserve thinking to maintain that state continuity, and turn-level thinking for that dynamic control over cost and latency.
And third, the huge performance gains that we saw in the benchmarks, which really validate the new architecture. That 16.5% jump on terminal bench, the 12.2% jump on the tool use bench, those numbers prove that the stability works in complex, real-world environments.
I think the synthesis is that GLM 4.7 really represents a refinement wave in how these frontier models are being developed. The focus isn't just on raw parameter count anymore. It's shifted decisively to architectural stabilization for agentic workflows. The goal is to make these long, complex, multi-step tasks not just possible, but reliable and controllable. It's a direct answer to the instability that plagued the last generation of models.
So what does this all mean for you, the developer or the architect who's been listening? We've established that the biggest performance leaps here are tied directly to the model's ability to execute, to use its tools. We saw that in the massive 41% performance spike on the HLE benchmark when tools were enabled. So given the really demanding hardware requirements for running this thing locally, needing hundreds of gigs of VRAM to get that full context and performance, that leads us to our final provocative thought for you to think about.
We've laid out the trade-off very clearly. You get unparalleled reliability and architectural control, but it comes at a profound infrastructure cost. So the question for you is this: what specific technical capability is it guaranteeing state preservation across a 50-turn debugging session? Is it dynamically disabling thinking to save 20 milliseconds on a simple query? What specific capability would justify the investment of, say, 4 96GB GPUs for your unique workflow?
The choice for the next generation of AI is no longer just between performance and capability. It's between architectural reliability and the financial cost of the infrastructure you need to support it.
Something to think about.
Think on that, and we will catch you on the next deep dive.